Now I am going to give few state transition diagrams for the time homogeneous continuous time Markov chain. You see the first example, it has only two states 0 and 1. So, the state space S is 0, 1, and the time spent in the state 0 before moving into the state 1, that is exponentially distributed with the parameter lambda. Once the system come to the state 1, the time spent in the state 1 before moving into the state 0, that is exponentially distributed with the parameter mu. Lambda is strictly greater than 0 and the mu is also strictly greater than 0. That means, you know, the exponential distribution has the mean 1 divided by the parameter. Therefore, the average time spent in the state 0 before moving into the state 1, that is 1 divided by lambda. The average time spending in the state 1 before moving into the state 0, that is 1 divided by mu. Since it is a 2 state, so over the time the system will be in the state 0 or 1, and you can classify the states also the way we have discussed in the discrete time Markov chain. Since both the states are communicating, both the states are accessible from each other direction, therefore, both the states are communicating each other. Since the state space is 0 and 1 and both the states are communicating each other, therefore, this is a irreducible Markov chain. For a irreducible Markov chain, all the states are of the same type. For a finite Markov chain, we have at least one positive recurrent state. Therefore, both the states are going to be a positive recurrent state. But here there is no periodicity for the continuous time Markov chain. Therefore, we can conclude the first example, both the states are a positive recurrent and the Markov chain is a irreducible Markov chain. So, the continuous amount of time system spending in state 0 and 1, that is exponentially distributed with the parameters which I discussed earlier. Now, I am moving into the second example. In the second example, we have a state space is countably infinite, and the system spending in the state 0 before moving into the state 1, that is exponentially distributed with the parameter lambda naught. Whereas in the state 1, the system can spend exponential amount of time, the amount of time spending in the state 1 before moving into the state 2, that is exponentially distributed with the parameter lambda 1. And similarly, the system spending in the state 1 before moving into the state 0, that is exponentially distributed with the parameter mu 1. Therefore, this is mu 1 and this is lambda 1. Therefore, the time spending in the state 1 before moving into any other state, that is going to be minimum of the exponentially distributed with the parameter lambda 1, one random variable, you can call it as a x, and you can call it as another random variable, that is exponentially distributed with the parameter mu 1. Therefore, the amount of time spending in the state 1 before moving into any other state, that just now we have concluded that waiting time distribution is exponentially distributed, that will come from here also. So, here these two random variables are independent, x and y are independent random variables. Both the random variables are independent. Therefore, the time spending in the state 1 before moving into any other state, that is going to be minimum of the random variable with the exponentially distributed parameter lambda 1 and the random variable which which follows exponential distribution with the parameter mu1. You know that the minimum of two exponential, as long as both the random variables are independent random variable, then this is also going to be exponential distribution with the parameters, with the parameter lambda 1 plus mu 1, as long as both the random variables are independent and both are exponential. You can do it as a homework. Minimum of two exponential are going to be exponential with the parameter lambda 1 plus mu 1. Therefore, the time spending in the state 1, that is exponential distribution with the parameter lambda 1 and mu 1. Also, one can discuss what is the probability that the system moving into the state 2 before moving into the state 1, that is a lambda 1 divided by lambda 1 plus mu 1. Similarly, what is the probability that the system moving into the state 0 before moving into the state 2, that is mu 1 divided by lambda 1 plus mu 1, that also one can find out. So, what is the conclusion here is the time spending in the state 1, that is exponential distribution with the parameter lambda 1 plus mu 1. Similarly, the time spending in the state 2, that is suppose if it is lambda 2, then lambda 2 plus mu 2. So, this is the one type of continuous time Markov chain. The third example, this is also continuous time Markov chain. This is sort of a two-dimensional Markov chain with the labeling with the 0, 0, 1, 0, 2, 0 and so on. So, all the labeling which is parameters for the exponential distribution. So, the change from the discrete time Markov chain state transition diagram and the state transition diagram of a continuous time Markov chain, here there is no self loop and the labels are the parameters for exponential distribution, whereas the discrete time Markov chain, it is a one step transition probability going from one state to other states. Here the labels, the arrow gives the time spending in the state exponential distribution with the parameter lambda naught and moving into the state 1 and so on. Now, I am going to find out how, now I am going to find out the Pij of t. For that I am going to do the derivation starting with the Chapman-Kolmogorov equation. Let me start with what is the transition probability of system is moving from I to j during the time 0 to t plus capital T. That is nothing but what is the transition probability, system will be in the state j at the time point t plus capital T, given that it was in the state I at time 0. That is same as I can in between make some other state. I can make one more state k at time point t. For all possible values of k also I will get the same result. That is same as I can make a summation over k belonging to S is a state space. That is same as what is the conditional probability of system will be in the state j at the time point t plus capital T, given that it was in the state I at time 0 as well as it was in the state k at small t also, multiplied by what is the transition probability of system moving from 0 to t from the state I to k. That is same as the first conditional probability. You see, this is same as the Markov property which we have discussed in the definition of a continuous time Markov chain. There I have discussed the CDF, cumulative distribution function. Here it is the probability mass function, whereas this is a conditional probability mass function. What is the conditional probability mass function of system will be in the state j at time point small t plus capital T, given that it was in the state I at the time point 0 as well as it was in the state k at the time point t, and you know that 0 less than t less than t plus capital T, because the way we made it is all these values are greater than 0. Therefore, by using the Markov property of a continuous time Markov chain, so this is same as what is the probability that the system was in the state k at time small t and move into the state j at the time point t plus capital T. Again you use the time homogeneous property. First you use the Markov property, therefore, this is the transition probability of t to t plus t moving from the state k to j. Then use the time homogeneous property, therefore, only the length matters, therefore, t to t plus capital T, that is same as 0 to capital T. Therefore, the system is moving from the state k to j from 0 to capital T, that is a p k j of t. The second one, it is a transition probability, system is moving from state I to k during the interval 0 to capital T. Therefore, this is I to k of t. So, this is valid for all I comma j with the t greater than or equal to 0 and capital T is also greater than or equal to 0. Therefore, the left hand side is the transition probability of system is moving from the state I to j from 0 to t plus capital T, that is same as summation over, I can rewrite in a different way, I to k in the interval 0 to small t, k to j instead of small t to small t plus capital T, because of the time homogeneous I am just making 0 to capital T. Therefore, this is valid for all values of k summation. This equation is called the Chapman-Kolmogorov equation for a time homogeneous continuous time Markov chain, because here for this transition probability we have used Markov property as well as the time homogeneous property also. Therefore, this is a Chapman-Kolmogorov equation of the transition probability of system moving from I to j in small t plus capital T can be broken into product of these for all possible values of k. So, like this you can break it many more ways with the summation for all for different state of k. Using these we are going to find out the transition probability of Pij of t. You remember, to find out the distribution of x of t you need a initial state probability vector as well as the transition probability Pij of t. The initial state probability vector is always given. You have to find out the Pij of t. Once you know the Pij of t, you can find out the distribution of x of t for any time t.